Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about lab power supply. So let's dive deep into it. So why the heck we need something lab power supply? Well, reality is our world runs on power electronics. Be it a laptop, be it a camera, be it a TV, be it whatever heck you. Everything around you requires power electronics at some point in time, including internal combustion engine at this point in time. So we need electronics. So let that be very clear. And that fundamentally means somebody is building it, and on top of that somebody is repairing it. Now you're like, oh, we don't repair it much. No, we may not repair it, but we still have to figure the damn thing out. It's like, why the heck it went poof, what went wrong, so the next iteration is not poof. So trust me when I say this, like a serious amount of work goes into a world where we can actually do those things. That requires a lab power supply. So you can test, repair them. And it's a must have. Like, let this be very clear. The moment, many times, even for people who are studying electronics and all that, electrical engineering and all that, many times that's the first project they do. And again, even teachers will encourage you, hey, build a quality power supply. That's a requirement, so to say. So it must, it's a tool that you are like, you're starting into your electronics journey. And why I'm talking about this, yes, because I do want to jump into it basic level, but at least I do want to try it on the side. So if you are going into there, you're gonna need it, like either for making or repairing. You're gonna need it one way or the other. This is one of those things that's like, let's say your laptop goes poof. How do you know it's the battery didn't went poof or the adapter went poof? Unless you have power supply. So you need that. And then what about the cost? What kind of money we are looking at? Well, you can start very low cost, like some cheap stuff. Like many people who are doing home electroplating and all that, they start with something very low. And you can even do DIYs where you can do some quite amazing thing. And then it can go so high up in price where it's like your kidneys have to go. So there is a lot of range in this because of its importance. So what are types available here? Here there are two major categories. There may be something else, but these are the two major puppy that we have right now. The first puppy that most likely that you're gonna see or most likely you're gonna buy as your first system is SMPS. Now SMPS is what we classify as switch mode power supply. So you take the AC power, you make it into high frequency, basically make it into DC, then make that DC into very high frequency AC. And that high frequency AC allows you to have very small Farad transformers, and then you control the output. So it does work. Now you may be like, why the hell you want to go through that much trouble? Well, this puppy is efficient. If you are old as me, as in like 30 years ago, you must have remember we used to have like consoles, like and TV consoles. They used to have huge adapters. Like those adapters used to be big and heavy. While your modern power adapters, which is for your mobile phone, that's far more powerful in terms of voltage and in amps, as in like grand total wattage, but it's still very light and small also. How? SMPS. Those old school transformers, they were flat out transformers. So we used to use transformers for everything. They were not very efficient, and especially if you're going down this low, it was not really that efficient. So you could be losing as much as like 50% at worst case scenario. So we've switched from that design to SMPS because it's far more efficient, and we can easily, if we design it properly, if the load is fixed, we can actually achieve a point where it's like 90% efficient or even more than that. So you take AC, you pulse width modulate it, and you get DC. It gives you efficiency and smaller body. So everybody wins. Now, we did this in all our world. However, in lab power supplies, ironically, linear power supply have survived. This is still there. We still have AC coming in, filtered and all that, and then goes into transformer, then gets stepped down. You're like, isn't that inefficient? Absolutely inefficient. Inefficient as hell. Most of these puppies have cooling fans that are running constantly. So yes, they are inefficient. However, if you go from that route, like AC to step down to DC, it gives you stability. And when you are designing a SMPS, SMPS is one of those things, it can be perfect. Like you can make a SMPS that is like GG perfect, but it requires you to tell it what you are designing it. Like if you are designing for laser diode, you have to tell the engineer, hey, laser diode, go. Because you can see there are so many topologies. Like you have non-isolated topologies if you are working in low voltage. You could have buck converter, buck boost converter, which allows you to increase or decrease. Buck only allows you to decrease, boost only allows you to increase. Isolated system generally used for AC systems where you have flyback topologies and forward topologies. Other topologies also, but these are the common ones. So there are a lot of options. When you're talking about linear, it's ironically simple. You take the basically a transformer core, step it down, rectify it, add capacitor to smooth it out, have another capacitor for high frequency noise, then have a voltage regulator, and have the output, again have a capacitor for stability and output. It's very smooth, meaning if you put this puppy built properly into an oscilloscope, it will be like me smooth, bro, me smooth. So that's why for majority of people, quality SMPS power supply, they're good, they're happy. However, if you are working in some scenarios where you're dealing with audio, you will not touch this puppy. You will not touch SMPS. You're like, no, sir. And that's the another reason why toroidal transformers are still manufactured. Audio people, they're like, we will not touch SMPS. Thou shall not touch SMPS. And there is actual genuine reason for that. So audio, and then you have talking about radio circuitries, they require what we call a low noise amplifier. So if your power rail is noisy, that noise gets amplified. So low noise amplifier requires a good power system. You can generally achieve it if you are powering everything from battery, but if you have to do it with AC, adapter noise is picked up. So LNA, if you're dealing with that, people will prefer linear. Medical system. Now, like, why is medical system? Aren't they themselves running on SMPS? Well, yes, they are running on it, but it's custom built for that. You are talking about a variable system. In variable, SMPS is not that great. So if you need what we classify as low volt RMS, meaning if you zoom into a oscilloscope feed and you're like, voltage rail is going like this, yeah, that's not acceptable for many things, especially laser diodes. Oh, those puppies are naughty. You do very high voltage RMS, you can cook them. LEDs also, like you can literally have a sloppily built power supply. LED could be bought from a quality manufacturer, let's say Philips or Cree. They can give you a quality LED that is like, bro, this puppy can last 10,000 hours, and you put it on a power supply, you're working, and 3 years later it goes poof. It's like, what the hell, how the heck LED got cooked? If you're lucky, generally power supply should get cooked, but LEDs will be like, hey, it's not, how the heck LED? Yeah, the voltage was noisy. And yes, that has happened. People like, and again, I'm reasonably sure most of you have seen where LED bulbs are dying rather than like, they're supposed to be immortal, but how the heck they're dying? If power rails are not clean enough, nothing will last, even the LEDs. And laser diodes, they are far more sensitive. So if your voltage RMS requirement is low, linear is the way to go. So for example, this is a very high quality power supply. Let that be very clear. If you're buying a Chinesium power supply, do not expect 5 millivolts of RMS. The moment you put load, you are looking at around 100 millivolt of RMS. So there is a genuine reason for people to prefer linear power supply even today. Heck, many of the high-end ones, they come in linear. So there is a genuine reason for that. So this RMS is the issue. You go to a transformer-based system, because there is no switching, inherently it's very stable. Like, and you are adding capacitors to remove whatever else frequency is there. So you can achieve very smooth. Like for example, this is a very high quality SMPS, 5 millivolt RMS. This is a very same brand, same power rating, but linear, it's 0.5 millivolt RMS. So be mindful. There is a genuine reason for going with this. And if you are dealing with something that is very expensive, do you really want to be like the reason why you fried it? Yeah, you fried it because you saved your money for like a cheap power supply. You really don't want to. So there is genuine reason for linear also. So for majority of people, shut up, buy SMPS, most likely because only those things you will be able to afford. But for other people who are dealing with something serious and naughty, they'll be like, yeah, we have to pay with the high price of fan noise and heat. But there is a benefit of that. So there are two types, we generally use them. Then we come to what these things control. Well, first thing controlling is constant voltage, meaning if you set the voltage to 30 volt, it will not go YOLO after that. It will be like, I shall stay at 30 volts. That's it. If you set it to 24 volts, it should stay at 24 volt. So constant voltage is a requirement. Now, why is that? Well, voltage is the driving force of electrons or electronics, meaning if I have a battery that's like this, how can I touch this and don't go poof? Well, the potential is not enough, meaning here to here is not high enough. I can touch this, not with my tongue. Do not do with lithium ion with your tongue. It will hurt because it's 3 volts and fully charged could be 4 volts. So yeah, it's gonna sting like a 9-volt battery. So voltage is the push. That's why we called it potential, like voltage potential. So that's the force of electronics. If you do not have voltage, you do not have anything. And the range requirement is bonkers. Like for example, if you are designing a circuit that's supposed to run on this, it itself could be designed in such a way where it's like 4.2 volts to almost 2.5 volt. It should be able to run. Again, that's a voltage range, a lot of voltage range. So for that reason, many times we require multitude, flexibility in voltage. You cannot just have, okay, 5 volt, 9 volt, 12 volt, whatever have you. That is not comfortable. However, sometimes that is required if you are dealing with a fixed load. For example, if you are working in an LED pipeline, you know all the LEDs that you are making is 12 volt. You may buy something like this, where it's like, a computer SMPS, and you just have a breakout board. And sometimes people open the box and go YOLO on it. That's up to you. If you are comfortable, do it. If you're not comfortable, don't do it. So people can, and sometimes people build a ginormous case where they have voltage rail, 12 volt voltage rail, 5 volt voltage rail, 3.3 volt voltage, and they also added a variable unit that allows you to control it. And you can see a lot of YouTube tutorials how to make a, easily, with a very easy, low component requirement, you can make those puppies. Be mindful, while the voltage rating is trustable to some extent, they are not stable. And the current rating, yeah, just don't trust the current rating. Most of them do not have the heat sinks, and not to mention the tuning requires to achieve that constant current without overheating the components. And thankfully, modern components have what we classify as a thermal shutdown, so they will cut off before self-damaging. But the current rating, I have seen YouTubers to be a bit more comfortable with current rating. Let's just put it that way. Voltage you can trust, current no. So variable voltage rail is far more preferable. That's why we want knobs, we want to control it. So you can make your SMPS, starting SMPS, and you just have 3 rails, 3.3 volt, 5 volts, and 12 volts. That's good. That's a good starting point. But sooner or later you're going to need variable, and variable is one of those things that you can just have a power supply. Kits are available for very low prices, and you can just buy one that is not very expensive. So this is the constant voltage part of things, where we start, and the power supply should not allow that voltage to be exceeded at any cost. There are only few electronic circuits that will allow that to happen, but it should not happen. Meaning this puppy like, no. I gave you 5 volts, that's it. You cannot consume 6 volt. So constant voltage. Then we come to constant current. Now this is where we separate men from the boys. So constant voltage, surprisingly easy. That's the first circuit that most people learn when they are learning about electronics. How the heck you manage the voltage. Current is the hard part. Now current, let that be very clear. Current is the driving, like the actual oomph, the actual work is done by current. So voltage allows things to be done, current does the thing. So setting it is the critical part. So what does constant current mean? Many times you may be like, okay, you are hearing this, like a laser requires a constant current, LED requires constant current. What does it mean? Like what physically happens there? Well, what happens is your voltage gets controlled. You cannot control current directly. You cannot be like, I give you 500 millivolts at 12 volt. Yeah, there is no such thing like that. If you have a LED, let's say, that is 500 milliamp rated at 12 volt, you give it 500 milliamp, it will heat up. Again, it will have some wastage, it will heat up. Over time, it will start to draw more, even if the voltage is the same. So you cannot control it. So how do you control it? You reduce the voltage. You have to have a feedback loop where it's like, bro, the milliamps are milliamp, amp, whatever the current is going outside of the bounds, and now you drop the voltage until it reaches the new stable point. So that's how we control current. Do not think controlling current is this new technology. No, it just stops the voltage down. If you have an oscilloscope, you can actually see it like happening in real time with power supplies, where you could just probe them properly and be like, okay, what if it starts to overheat? Okay, LEDs specifically, you can see that, okay, 12 volt, it start to heat up, 11 volt, start to heat up more, okay, it start to drop, and then it will drops to such a point where it becomes efficient again, and then it's like, me good. So voltage dropping, and it also allows to protect against short, meaning what if positive and negative rail are shorted, let's say your MOSFET blew or something like that. The constant current here comes to the rescue. It's not as fast acting fuse, but good designs could be still be safe, where it's like, hey, it's detecting a dead short. Why? It's like, hey, I'm supposed to give you 500 milliamps. Yeah, whenever I increase the voltage, you start to draw more than that. So you can start the current, voltage starts to rise, voltage, it reaches 2 volt and it's like already draining 500 milliamps. It's like, whoa, it clamps it down. That is the primary reason why you can have a test board that has expensive components. You can safely power it with a lab power supply, specifically with constant current. If you fry something, only that thing will be damaged. It will not cook the whole board. If you do not have constant current, it will cook the whole board. So if you have a computer power supply 12 volt and you are working with something, and this happened where something shorted, it will draw full power of the power supply as long as power supply allows it. And if you are working at, let's say, 2 amp, power supply was rated for let's say 10 amps at short circuit scenario. That's why every electronic engineer, thou shall have constant current. You need constant current. Must have for serious power. For example, if you're charging the LEDs, this 18650, how the heck we charge you? Well, we do this. So you can see what we have, constant current. So for example, this is a 1 amp cell. So I want to charge it at 1 amp, generally 1C charging. So I will give it a computer. It's like, bro, give me this much amps. So it's like, okay, amp is fixed. Everything is fine. Everything is dandy. But here's the, you will notice voltage is here. Why? It's computer started to give voltage in order to get things going. And it noticed at low voltage of 3.3 volt, it is already reaching its target amps. So it's like, okay, I'm going to stay here. And then it's like, the amps are going down. So it's like, okay, increasing the voltage, amps are stabilizing. So increasing, stabilizing. So it reaches a point. Then we switch. So at that point we reach constant voltage. So at that point is like 4.2 volt. You can notice current drops. Invert happens when you are doing constant current. So same thing. So in constant current, voltage is rising to match up in case of batteries. And then after that we use what we call a constant voltage. So milliamp goes down until it's fully charged. So constant current, that's the key. And that's why you cannot just like directly swap a lead acid battery system with lithium ion. Lithium, even with BMS, they are not doing this. Lead acid is inherently designed with constant voltage. They're like, this is the voltage, go YOLO. Lithium do not like that. So you can force it. BMS could try its best to handle it, but it won't be a pretty situation. It may even go boom. So that's why constant current. You will always hear this word with LEDs, laser diodes, lithium ion chemistry, constant current. Now let's talk about the quality aspect of it, because again, you must have seen it in Amazon where price starts at very low price to, are you kidding me? Somebody is really paying that much money for a power supply? Like, I dare you. I dare you to look into power supply like this, like Roche and Schwarzenegger price. And yeah, kidney is cheap for these things. Like they literally reach a point where it's like price is not available. You literally have to get quote. So it's super duper hyper expensive. So it starts with cheap and it goes blank check level. So why is that? Well, primary reason is noise. So whenever you are working with something very expensive, let's say you're working with fiber laser diodes, those puppies are expensive. Would you risk those expensive puppies, which could be a few thousands of dollars, to with like, yeah, I saved money and I fried them because I used a cheap power supply? No, hell no. You'll be like, hey, big puppy. And if you are doing this regularly, you will be like, dude, this is a bread and butter. You will pay for this, even though it's like $15,000 or more than that. You will be like, shut up, take money. So noise, basically voltage RMS is the critical requirement. You can see many Chinese quality power supply. Put a load, put it under oscilloscope, you know, like, holy hell. It's like on no load, it's like, hey, 5 millivolts, man. It's everything cool. Put load, it's like 100 millivolts. Yeah. No. So having stable basically noise at varying load, that's the requirement. So if these companies say this is the noise, the end, you do not have to check it. Of course you should check it, you should verify it in case you get a defective piece, but it's like done. It's like, oh, what if I'm drawing 50% of its power? It will be the exact same. What if I'm drawing 100%? It will be the same. So noise is the expensive part. So you can go from Chinesium to something like this, signal to and something bonkers. So generally the biggest difference you will notice directly is noise under varying loads. If these things say we are stable, they are stable. If this thing says stable, they do their best. Chinesium, good luck. So that's up to you. Then another feature that allows the price to go lol is multiple isolated individual power rails. So you will see in cheap one, only one positive negative. Here you will see positive negative channel number 1, positive negative channel number 2, positive negative channel number 3. And in this puppy, you can see 4 of those puppy. Do not ask me why European have this weird thing where they have red and blue. I have no idea, but they have red and blue. And you're like, why the hell they have black leads next to them? Those are for what we call 4-wire voltage measurement, meaning it allows them to bypass the power wire itself. So they are bypassing the power wires, so to say, resistance. So that allows them to, it's like, hey, do you want 5 volts at your circuit? You want 5 volt at your circuit? Okay, I'm gonna compensate based on the readings of that, how much energy I'm losing. So it may be like, hey, the wire itself is eating up some voltage. So they will be like, hey, 5.001. It will adjust based on the sense wire. So you need sense. That's why the expensive ones have that. So you have power rail and sense wire. Sense wire allows you to, sense wire does not have to be same amp rated. It just need to be enough to conduct the voltage, where the meter inside the system where it's like, ah, I see. So independent isolated power rails. And then we come to the most painful word for any businessman, precision. Because here's the deal, you can get everything done, child's play. Add word precision to it, price goes lol. Like, sir, I want a sphere of this quality. No problem, sir. Take it and go, sir. I want this sphere at this tolerance, as in increased precision. Yes, sir. Blank check, sir. I want super high precise. Yes, sir. It's a 1 in a billion kind of thing. Yeah. The more precision you add, the more price goes. These things, they have super duper precise meter reading inside. Now, does that matter? Absolutely. Do you really want to be working in a hyper expensive equipment and wasting time? Okay, I'm probing. Am I exactly getting this system? No, hell no. You're like, hey, I tell you, give me, let's say, if you're working with USB-C power delivery, 48 volt, you want to be damn sure it's 48 volts. So if this puppy says 48 volt, it is 48 volts. So precision matters, or not only of output but also of measurement. These things have internal measurement unit that are genuinely good. Where it's like, unless you are using some very high grade calibrated meters, this thing will bitch slap most meters. And that's why like there is a whole another ecosystem of 7-digit, 8-digit multimeters, which are like, do not even look into their price. They are like, what the hell? The prices are bonkers. Those things can compete with this. But if you're like, hey, my bench, $10, $20 meters, is like, bitch, please. This will be like, bitch, please. These are also temperature compensated. So if they are within their operating range, like some are rated super bonkers. It's supposed to be used in an air-conditioned room, but they built it like it's supposed to be able to run from -10 to 60 degrees Celsius. I'm like, human won't be there if you do it. The assumption is like, what if you put in a cabinet and cabinet cooling fails? So they are designed to be a bit more robust. Now, precision, again, precision is a rabbit hole. You can keep going down. Like, to give you a context, how expensive these things get. CERN, super collider. The meters they required was so expensive. They are like, yeet. They made an open source meter. They are like, we cannot afford these meters. We just have to open source it. I'm not even joking. That happened. So you have to know the precision is expensive AF. And then we have data logging, which I personally hate every YouTuber for this. It's like they're making, oh, I'm making this power rail. So many amazing design, and none of them have actual data logging. It's like, dude, without data logging, you are nothing. It's the same thing the great Adam Savage said. It's like the only difference between science and screwing around is writing things down. For example, let's say I have 2 lithium-ion cells. How do I know which has better charge characteristics? I have to write it down. Basically, I gave 1 amp, how quickly the voltage ramped up, how long it took. If I have a system where I can log all that data, I can easily say A is better than B. And again, you can even add other instrument also where you can have temperature. That will be a very good indication. Temperature, voltage curve and all that. If you're not logging it, what the hell are you doing? So logging is surprisingly easy to do, but it's not taken seriously for some reason. But if you're starting to pay some serious amount of money, you will get it. Like even Signal has this, Ronald has it, and these things also have it. Many brands have it. And again, be very mindful. If you're buying some Chinesium system, please check any YouTube video that has anybody actually worked with that, because while having a microcontroller that has serial output, that's super easy. Almost all do. Having a serial to USB protocol converter, that's super easy to do. Building a software which actually reads what is doing the USB protocol in a usable manner, yeah, that's the hard part. So not even hard. That means somebody has to actually sit down and develop it. So whenever you are buying from brands like this, they have all that system, and many times they sell the whole kit. So you will have electronic power supply, you will have electronic loads, all that jazz for that reason itself. So all the data goes into one software pack and you can analyze everything. So data logging interface is a big system, and that's why like branded one, they will have a lot of parallel channels, USB, Ethernet. Why the heck they have Ethernet? That's the reason for that. So you're supposed to able to properly data log everything. So, and because of these things are generally very high precision meter, they're actually good. They're actually useful. So that's why, that's how your price goes from okay to lol. I genuinely hate nobody has built it so far in Arduino. I should build it. I have no idea how to, but I will try. So this was my presentation on lab power supply. Hopefully you have liked it, learned from it. In that case, please like it, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.